Welcome to everybody. I'm going to present a work for code protection, and in particular, an approach that we proposed for obfuscating code by specializing interpreters. The main idea starts from two key observations made on obfuscation. The first one is that obfuscation is a well-known program transformation technique for making programs incomprehensible for observers. It means that we want to make the observation of programs difficult and hard to understand for external observers that need to perform some kind of reverse engineering. And in the literature, this has been formalized as a problem of completeness. And in particular, it's been observed that making, whenever the observer is implemented, is formalized as an absolute interpreter, then obfuscation means to make programs incomplete with respect to that analysis. So this is the first point, the connection between the model of attacker given by as abstract interpreter and the incompleteness, the imprecision of the abstract interpreter for the program semantics. The second observation is a connection between obfuscation, transformation, and the specialization of programs of interpreters. In particular, the idea here is the observation that it is possible to transform programs in a way which preserves semantics by specializing the interpreter on the program. This is because the specialized program inherits the structure, the syntactic structure of the interpreter, and while keeping the same semantics of the original program. So on this observation, we can say that it is possible to obfuscate programs by specializing interpreters that has been distorted, transformed, in order to induce, connecting to the previous observation, to induce incompleteness of an observation of the program. So these are the main ideas, and in order to exploit these two observations, these 2 points, in order to obtain an obfuscation technique, we have to answer to 3 questions. To solve 3 issues. And in particular, the first one is we wonder how we can make an interpreter distortable. So what it means to make an interpreter distortable. In order to get this, to solve this problem, we provide a formal model for interpreter, identifying the 2 different phases of interpretation, and which allows us to identify precisely where we can distort the interpreter, so where distortion may intervene. The second issue is to observe how can we obfuscate program, indeed, by interpreter specialization. So how the obfuscation can be performed by distorting interpreters that can be specialized. And in this case, we define a new notion of optimality, which comes from the Jones-optimality on time complexity, which provides us with a bound between incompleteness, specialization, and interpretation. And it allows us to connect all these observations and to provide our approach. Last, we have to understand how we can drive distortion of program interpreters in order to indeed obtain an obfuscation. And in this case, we put all together, and we can drive distortion by means of incompleteness. Namely, we transform the interpreters in order to induce, integrate code with some features, syntactic features, that makes the analysis incomplete. So let's start with the first point. We observe, sorry for the conversion, there are some mistakes in the conversion from Keynote to PowerPoint. So the idea is, first of all, we observe that we can split the interpretation phases in 2 phases. The first one is the syntactic parser, where we just check whether the program is in the language we are interpreting. Then we generate the control flow graph of the program, and then we apply the semantics execution, which is the semantic interpretation, providing us the output with respect to the input of the program. So the first step is just which model can we use for parsing the program. And the idea we exploit is to use symbolic machines for modeling the parser. What is a symbolic machine? A symbolic machine, we have here an example of Automaton, is just a finite state automaton where the alphabet may be infinite. So we, instead of labeling edges with symbols, we label edges with predicates. So we have a finite set of states, we have an initial and a final state, then we have a recursive enumerable set of input predicates on this potentially infinite alphabet. So if, for example, we have our language, which is the regular language on the bottom of the slide, then the predicates are just the possible predicates for the language. So an assignment, a guard, or any symbol we have in the language. And then we can have also stacks for example, for checking, as in our example, in our language, the balance between bracketing. And again, we have an alphabet which may be potentially infinite for stacks. And we have a recursive enumerable set of predicates for this alphabet. Then we may have a set of stacks, maybe 0 or more. And finally, we have a transition relation. Transition relation is, it takes an input state, it takes a predicate on the input alphabet. So we're supposed to have an input tape with the strings we have to accept. And in the edges, we have a predicate. So we accept, we follow an edge if the symbol we are going to read satisfies the predicate. Then we have n is the number of stacks. So if we have a predicate for each stack for the element on the top of the stack, and we pop that element then when we apply the transition. Then we have, it is potentially a non-deterministic automaton. So we have a set of states. In this case, we have only one because it is deterministic. We have a direction. So in general, we can move right, left, or we can stay. We can stop on a symbol on the tape, on the input tape, like a Turing machine. And finally, we have a string of symbols for each stack that we push on the top of the stack. This is the main model. So, for instance, this is precisely the model of the parser for our language. Just let's see on an example how it works. So, the visualization is not precise. Anyway, we have we just read one symbol at a time, and we apply the transitions. And the idea is just whenever we use the stack for checking the balance of bracketing. So whenever we reach we enter in a non-deterministic choice, like in this example, you see the symbol red. In red is the symbol that we read indeed. So there is, it was okay before, but not in this PowerPoint. And so when we enter, we just put on the stack the symbol, meaning that we open the brackets in order to be sure to find the closing brackets before ending the parsing. Then we continue, we do the same when we enter in a loop, and so on. When we exit from the loop, we just erase the symbol from the stack, and we go on. And when we arrive to the end of our string, we also find the closing bracket for the non-deterministic choice. And when we reach the end of the string, the stack is empty, and therefore the string is accepted. If, for example, we don't have the closing bracket for the non-deterministic choice, then when we reach the end of the string, we have on the stack something which is different from the bullet, and therefore the string is not accepted because the balance was not respected. We don't consider simply automaton, we consider also transducers. Transducers are like the finite state machine we introduced before, but with a function providing also an output. So we have a function taking in input the symbol we have on the tape, we are reading on the tape, and providing in output a sequence of strings that we generate. In the notation, we have the association between the input and the output symbols, the movement, so left, right, or halt, and the transformation of the stack, which is the symbol read on the top of the stack and popped, and in the case, the symbols that we push on the stack. Again, let's see it on an example. So in this case, the transduction generates in output the sequence of guards that has to be evaluated. and of statements that has to be executed. Moreover, if we keep the graph structure, what we obtain is precisely the control flow graph as a transduction. The graph we obtain should be minimized. I keep graphically minimized in order to be easy to read, to observe. So we just scan the string as precisely as before. We use the stack as before, but as you can see, when we read a statement or a guard, we just keep provide the same in output, and in this way we design also the control flow graph. This transducer is non-deterministic, so in this case we decide to take the branch on the left of the non-deterministic choice, and we decide to enter in the loop, but then we can choose to continue without re-entering the loop, or at the end, in order to have all the possibilities, we can decide just to skip the first part of the non-deterministic choice and to take the second branch. When in order to have the whole control flow graph, clearly I have to follow all the possibilities. So as you can see, when we reach the end, what we obtain in output by the transduction is a partial interpret evaluation of the program, which is precisely the control flow graph. So what we call this transduction execution sequence extractor, since it extracts precisely the sequences of instruction or cards that will be executed in the control flow structure. So now that we have the model for the parser, we can decide how to model a semantic execution in order to have a complete model of the interpreter. And in this sense, we define an interpreter function precisely on the language. So we have a control flow graph to interpret. We have three possible labels. So we have three rules: one for skip, keeping the same state; the assignment, modifying the variable of x, the value of x; and the guard, just filtering the states that satisfy the guard. Then we can define a function applying precisely these rules on the labels of the control flow graph, and the least fixed point of this function is precisely the semantics of the program. So let's see again on very quickly on the example, on the running example. Suppose to start from x equal to 2, then we just propagate on the control flow graph the value of x, and we observe that we will never take the edge from 1 to 4 because the value of x is greater than 0. So we propagate the fact that part of the graph is not executed, while we enter in the loop, and so we compute the fixed point, and at the end we have that the exit value is precisely 0 for x, in this case. If we start from a negative number, we just took the other branch at node 1, and while we'll never follow the direction towards the node 2, and then at the end, we have that x at the end is precisely -1. Okay, now that we have a model for interpretation, we can understand where we can distort this interpreter. And the idea is just to put on the top of the parser a distortion, so a model of something that is transforming the program in order to to obtain a new program which is semantically equivalent to the input one, and on which we can apply precisely the same parser, the same execution, semantic execution. This distortion is indeed a symbolic finite state transducer, which just transforms part of the code in the same language. So simply adding some features that induces the idea then will be that induces incompleteness. In general, just adding some feature to the program. And the basic constraint is that clearly this transformation has to be semantic preserving. So the P prime we obtain has precisely the same behavior as P, and it is written in the same language, so then we can apply the syntactic parser we have defined and the semantic execution we have defined. So this is the model of interpreter on which we work. And just an idea, a trivial distortion schema, we have the function fb and fc, which are simple syntactic transformation preserving the semantics. And then whenever we reach a guard or statement, we just transform it and it provides in output the same sequence of statements, but with the transformed expressions or assignments. So we just follow the string, read the whole string, and each time we reach a guard or a statement, we have we provide in output the transformed syntactic element. So that is the model we use. Now we have to understand how we can exploit this new notion, how we can define and exploit this optimality for driving the distortion. So the idea, spec should be on the same line. The idea is that we have a specializer that takes an interpreter and a program and provides in output the specialized program, the specialized interpreter on the program, which is a new program, as I said before, inheriting the structure, syntactic structure of the interpreter, but with the same semantics of the program. And the Jones-optimality is a property of specialization, a relation between specialization and interpretation, saying that a specializer is optimal when the time complexity of the specialized program is less or equal than the complexity of the original program. Instead of observing time complexity, we decide to observe the abstract semantics, and therefore we call abstract optimality just the fact that the specialized program has the same semantics or a more precise semantics than the original program. Whenever we decide to clearly, it may be quite hard just to improve the semantics, so we can just weaken this constraint by asking the equality, and the equality we call the equality abstract suboptimality. We can observe that if we consider concrete semantics instead of abstract semantics in this equation trivially holds because it's precisely the definition of specialization. The semantics has to be the same. But when we move towards an abstract semantics, then it may fail to for programs. What we proved is that if the domain, abstract domain, is complete with respect, the domain is complete with respect to the specialized program, if and only if the specializer is suboptimal with respect to the interpreter and the program. We can look at this result on the opposite side. So we can say that if the domain is incomplete for the specialized program, if and only if the specializer is disoptimal, so it is not optimal, with respect to the interpreter and the program, where disoptimal in particular is defined as being more abstract. I mean, if we specialize the program, then we obtain something which is more abstract, less precise than the original program. This means that we can obtain an obfuscation of the original program if we specialize an interpreter with respect to the program and the specializer is indeed disoptimal. It is clear that disoptimality is a property that depends on the specializer and on the interpreter, apart from the program, which is our input. So we could decide just to fix the interpreter and to look for a specializer which is disoptimal, or we can decide to fix the specializer, and in particular, the generation of the control flow graph is indeed a specialization of the interpreter with respect to the program, since it just partially evaluates the program by looking at the control flow structure, and we we distort the interpreter in order to introduce features that makes the resulting program then an obfuscation. So this is the idea of distortion, and the optimality suggests precisely the connection that optimality creates between the specialization and the completeness, suggests us just to exploit distortion for integrating the program with features making the static analyzer, the observer, incomplete. In order to show how it works, we see it directly on an example. And in this case, we choose data obfuscation, which is an obfuscation technique described, characterized by Drape in 2004. And in particular, we consider parity obfuscation. So the idea is just to make the parity analyzer incomplete, imprecise. So how can we make the analyzer imprecise? We can simply transform the variables by multiplying by 2, since in this way the parity is completely lost. Clearly, in order not to change the semantics of the program, we have first we multiply by 2 all the variables. Then each time we access a variable, we have to divide it by 2 in order to get the right value. And each time we store it again, we have to multiply by 2. And then at the end of the program, we have to divide by 2 all the variables. So for this reason, the trivial schema I used before is not sufficient. We have an initial part looking for all the variables in the program. And so we have initial scan here, we have only one variable, and we put on the stack S. And then we use this variable just to insert the initial set of assignments, multiplying by 2 each variable. Then we can transform the whole program. So each access is divided by 2, and each assignment is the access divided by 2 and the store multiplied by 2. And then we transform the whole program. And when we reach the end of the program, we just use stack iota, which was used in the beginning, filled in the beginning, just to know for which variable we have to define an assignment divided by 2 the result. And so in this way, we obtain the final transformation, which has an initial set of assignment, the final set of assignment, and in the middle, the transformation of the code, which where the parity analysis is completely obscured. I mean, it cannot get the parity of the variables. So this is the main idea. And at this point, this is the distorter. We can combine this transduction with the sequence of execution extractor, I said in the beginning. In this way, we obtain precisely the control flow graph of a transformed program, which is made of, which is an obfuscation of the original one. So concluding, what we propose here is a technique for obfuscating program by specializing interpreters that has been distorted in order to, as I said, integrate in the code some feature that makes the analysis incomplete. The limitation of this work is that it is built only for obfuscation working on the transformation of the code, so on syntactic transformation. And so the idea could be in the future just to understand whether we can use distortion instead of using it on the top of the parser. We could distort the semantic execution, and just to see whether this allows us to handle also obfuscation dynamic techniques, dynamic obfuscation techniques, such as those based on self-modifying code. Moreover, we would like also to, from the practical point of view, we don't have an implementation, so we would like to implement at least the technique we have modeled in this way. We have the parity, we have the flattening on the paper, but we also model the slicing obfuscation in this context. And from a theoretical point of view, we would like also to better understand the meaning of absolute optimality in order to understand how the intentional nature of code indeed affect our way of analyzing code. That's all.
Any questions from the audience?
Change it. It's gonna be a really good question. Wait.
Does this work?
Yes.
I think it's a really cool insight that you model the observer as the abstract interpreter, and then you deal with incompleteness. I think that's really nice. I wonder, have you looked at how? So intuitively, you could have many obfuscations, and you could compose them together. But according to your theory, it might just be that one obfuscation is just as good as another because it's either incomplete or it isn't incomplete. Is there a way to quantify the difficulty of the use of abstractions? Should you compose them all together? Distortions, I mean?
I mean, we didn't work in composing obfuscation. I mean, it depends if I don't know if I understood the answer, but the question. But anyway, the idea would just to, if you want to obfuscate with respect to a composition of observations. I think you mean. I mean, when you want to compose obfuscation, you mean to obfuscate with respect to a composition of a different possible observers, right?
I asked the question badly. I guess all I'm saying is, if the drape example that you did at the end, where you multiply by 2, if I imagine a real human being doing deobfuscation work, they'd be able to figure this out, right? So you could imagine trying to make more and more complex transformations that are harder and harder for someone to make sense of, an observer to make sense of. And so I guess the question is, how do you scale up your technique so that you can model that composing obfuscations leads to more undecipherable code as a result?
I mean, it depends on what makes the observer incomplete. So if we have if you want to model more complex obfuscation, always we have to perform obfuscation with respect to an observer. So we have to fix the observer for which we want to make the obfuscation, and then we derive the obfuscation. So it's the opposite, perhaps. I mean, we don't start from the obfuscation; we start from the observer, the model, and then with this approach derives the obfuscation for that observer. So if the observer, I mean, depending on what the observer indeed is able to analyze, we can characterize the features making it incomplete. There will be always something that makes the observer incomplete. And from this point of view, I don't see how, if there is really a problem of scalability. I mean, because it depends on the observation. It may be, it may be really complex, but anyway, I mean, we have to find something that he's unable to observe precisely. So I don't know if I answered your question, because I see
that's
just
good. Thank you.
a different direction on.
I understand the point you're making. I guess the follow-up question is how much experience or what's your intuition about formalizing an abstract interpreter that represents a realistic observer?
Well,
again, I'm just thinking, there's people whose full-time job is to reverse engineer software. They use all kinds of tools. They have lots of ingenuity and insight. And it seems difficult to me to imagine expressing that process as an abstract domain. I'm curious if you've thought very much about it.
Flattening, for instance, is a real technique of obfuscation, and we modeled as an observer, an abstract observer. I mean, we characterize what the observer has to observe and which kind of observers flattening is deceiving. So flattening, slicing, obfuscations are all real obfuscation technique that we're able to model as obfuscation in this context. So with an abstract interpreter, model observer deceived by that techniques.
Other questions? Then maybe I can ask a final question. So how calculational is the approach? Can you mentioned retrofitting existing obfuscation techniques in the framework? Can you actually derive new techniques by looking at optimality as a driver for some calculation from?
Yeah, sure. I mean, if we are able to model the observer, I mean, we start. It depends on the way we model the obfuscation problem. The obfuscation problem that we are able to approach in this case is just a problem given by the point of view of the observer. We fix which is the observer that we want to deceive, and then we can just build all the structure. I mean, we find which are the syntactic features that observer is unable to observe precisely, and like the multiplication by 2 for the parity observer, and then we can distort the interpreter adding that features, and at that point we have the obfuscator. But we have to start from the observer we want to deceive. The problem has to be formalized from that point of view.
I'm wondering how much guessing there is in this part where you introduce the new features, the features that you use to distort.
Well, there exist techniques from transformation techniques for understanding what makes incomplete an observation, but there are some. I mean, a small amount of guessing, which is reduced at minimum. I mean, the first work at Python 12 was guessing completely. Now we just reduced at minimum amount of information to guess, which is not really guess. I mean, it's formalized what is incomplete with respect to an observation.
Right.
But in the syntax we have, just it depends on the language what we have to add for making that observation incomplete.
I see. If there are no other questions, we can conclude the session. Thanks to the speakers for taking the time